All right, so video system's ready to go, so we'll move on. Our next speaker is Marta Kwiatkowska, and she'll be speaking on model checking and strategy synthesis for mobile autonomy. Thank you.
Good morning, and first of all, thank you to the organizers for inviting me. This is a wonderful place. I'm sure I'm going to enjoy the next 2 months here. And of course, I've only just arrived, so this is a great opportunity for me to introduce my research to you. So like the previous talk, this talk is also going to be about logic and probability. But there are differences, because I don't come from the AI background. I work in formal verification, in computer-aided verification. So the logic is going to be temporal logic rather than first-order logic. And the probability is not going to be for data. The probability is going to be used in, to represent the system dynamics. And also another contrast, it's not going to be Bayesian, it's going to be the frequentist interpretation. But there are similarities, and the similarities in that I also want to work on software tools, and this is the subtitle, From Theory to Practice. There will be a software tool which is an extension of the PRISM model checker that was developed in my group, and this talk is going to be about my new project, what we are working on, and I will also say something about where we are going, and I hope I can get to that last slide. I can also identify some gaps, perhaps for verification people. Okay, so first of all, I think it should be fairly clear to you that there has been tremendous progress in mobile robotics in terms of technology. I think we heard deep learning mentioned. So mobile autonomy is here, and it is for real. Robots don't just, clean the floor for you. People are inviting them into their homes to take care of the elderly. And of course, it's very appropriate for around here, the Google car. That's a self-driving car that has been introduced. And it's not just Google, Uber and Tesla are doing the same. And I wanted to start by asking the question, are we safe? Of course, I'm dramatizing a little bit. You do not want to see a blue screen, when you are driving, you are riding, not driving, you are riding in a Google car. But in fact, what they do, maybe they don't produce the blue screen, but what they do, what the Tesla does, is simply hands over back to the driver. Of course, I say imagined or real, and if you have been following the news, the Google car crashed into a bus, but Tesla has been in the news even more because there has been a fatal crash of its autopilot, and it is currently being investigated. So what do people like me want to do? Well, first of all, inside each such device, each such robot, self-driving car, etc., there is software, and we want to make sure that this software is predictable and it is safe to use. For example, there will be component failure, and there will be environmental uncertainty. What we want to do is we want to quantify it probabilistically and then develop methods that can express quantitative, probabilistic, and other types of quantitative properties and bring in quantitative verification. So model checking, which employs temporal logic, but in conjunction with probability. So quantitative verification employs quantitative formal models, and I will say in a minute what that means. You can get these models, you can extract them from code, you can use them at runtime, and you specify goals and objectives in temporal logic, but with probabilistic information in them. So you can talk, in addition to temporal logic, you can also talk about the probabilistic quantifier. So for example, the alert signal will be delivered with high probability in 10 milliseconds, if you are talking about in-car communication. Now, the focus of my work has been on model-based design, automated verification via model checking, and more recently also strategy synthesis. So the overview of the framework is as follows. Now, the idea is that we want to model the Google car. I mean, it's a vision, it's a very ambitious goal. At the moment, we are modeling components, so you can have, probabilistic failure, for example. Now, the idea is that these states are discrete, but to link up with the previous talk, they can actually be probability distributions. Probability distributions over the states if you have uncertainty. But the probability distributions there represent the dynamic, so they tell me about the probability of going from one state to another. I also have a probabilistic specification, and that probabilistic specification simply says the probability that eventually within time t I'm hitting a crashing state is small, okay? Small, perhaps not small enough for most of you. I think we would want to have something like 10 to the minus 5, 10 to the minus 6. Now, if you have a model and a specification, you put it into a probabilistic model checker like PRISM, you can get answers. Yes, this is satisfied. No, this is not satisfied. And you can also obtain a strategy. From a specification, you can obtain the strategy for the Google car for going from A to B. Now, historically speaking, probabilistic verification goes back to the 1980s, where the first algorithms were introduced in the context of LTL, but first implementations came later. And in fact, PRISM is a tool that was developed around 2000, so it's 2001, it's 15 years old now. But in the last 15 years, there has been a lot of progress, and the tools have matured, and the usage has increased in, the probabilistic model checking is used in many, many different areas. But the question I wanted to ask in this talk is, which modeling abstraction should we use for mobile autonomy? There are many, many probabilistic models. Many of you would know about Markov chains. So I have discrete states, and I have perhaps discrete probability distributions that tell me how to move, with what probability I move to the next state. This is not sufficient in many cases, so you may also want to include decisions where there is a choice, perhaps, between probability distributions. But of course, that discrete states, discrete probability, do not represent the real physical world. So we also need to bring in continuous real time, and also continuous space. And you may want to have, continuous space as well as discrete mode switching. But is this really what mobile autonomy demands? Now, mobile autonomy is about autonomous systems. So these are systems that continuously interact with the environment. But the environment can, of course, include other cars, pedestrians as well. So the environment itself is active. It is not passive. Because mobile robots are autonomous, they have their own goals and their own objectives. And these goals and objectives can conflict with the goals and objectives of the other agents in the environment. And of course, they also take decisions depending on, where they are, depending on the current state. So it's very natural to adopt a game theoretic view, where the player for the Google car is the car itself, and the other players in the game are cars in the oncoming traffic, and other also pedestrians. And in fact, there are many occurrences of games in practice. What I'm stressing here is that I'm taking stochastic games and putting them in the context of modeling the dynamics of mobile robots. So what makes a game? Well, first of all, there have to be players, and you can talk about n players, and the players will take turns, or perhaps they will be concurrent. Rock, paper, scissors is an example of a concurrent game. But crucially, I'm going to work with games which are stochastic. So there is also an element of stochasticity which comes perhaps from uncertainty, but it may also come from randomization, where you use probability intentionally. There is a value payoff for a game, and of course the key question that we study in games is, does there exist a winning strategy, and if yes, can you construct it? So you might say, well, what does this have to do with the Google car? Well, I can show you a news clip. This is what Google actually responded following the car crashing in a bus, and of course they are realizing that the issue is more complex, and for cars to actually merge into traffic, they will actually have to explicitly negotiate with the other players of the game. So what this lecture is about putting forward stochastic multiplayer games as a modeling abstraction for competitive behavior in the context of mobile autonomy with adversarial environments. And why stochasticity? Because there is failure, and also because there is uncertainty. Autonomous cars actually have to employ perception modules, so they have to work constantly with sensors, and these sensors are actually going to give me probability distributions because they are going to be uncertain about where. So I will introduce a temporal logic with a probabilistic quantifier for it, but I will also stress that it is not enough to work with single objectives. I'll try to argue for what we call multi-objectives, and I will mention that there is a tool called PRISM-games 2.0, and I'll finish off with some future challenges. So what is a stochastic multiplayer game? Well, I have multiple players, and these players can take decisions. And the idea is that they play against each other. But probability comes from either failures or, as I've mentioned, noisy sensors, or also randomization. Now, the games that I'm considering here are actually very simple games. They are turn-based. I don't even consider concurrent for now. They are discrete time, zero-sum, and complete observation. There is much work in game theory which has developed techniques, algorithmic techniques, for much more complex games. But I'm just shamelessly focusing on the work in my group because of the tool. The tool is currently limited to these types of games, but they are widely studied. So I've mentioned mobile autonomy, but of course distributed coordination or security is another example where you have a game between a defender and an attacker. So a stochastic multiplayer game, in my case it is a turn-based game, you can think about it like an MDP. I have finitely many discrete states, but these states are partitioned amongst a number of players, and I'm representing them here in terms of colors. So because this is a partitioning in a game, in the turn-based game, every state is controlled by exactly one player. So I can think about it as an MDP with an additional structure of multiplayers. Now what a player can do is can choose between actions A and B, but each action is a probability distribution explicitly representing the fact that you can have a correct and a failure, the correct behavior or a failure, for example. You can also annotate these stochastic games with rewards or costs, and I'll just mention here an example where these rewards and costs are simply annotations of the states or actions, and in this simplified case they are going to be non-negative, but this is not an essential restriction. Now for games, what I want to do is I want to talk about a variety of objectives. The simplest kind of objective is, I suppose, probability, probabilistic reachability. What's the probability of reaching a particular state? But the reward-based objectives include expected total reward. So if you are in a computation, you want to sum up the reward along the computation. But you can also talk about mean payoff. What's the long-run average, which is the reward divided by the number of steps, or a ratio reward. Think about the reward per unit time. So you have a ratio reward where you divide the reward by the amount of time. There are many, many more. I'm not considering them here. So I have a game. I have a turn-based stochastic multiplayer game where I have n players. To represent the behavior, the dynamics of that game, I will start in the initial state, and then I will unfold it into the set of all the possible infinite computations, where each computation is an alternating sequence of states and the actions. The action which is the choice that has been made. Now, a strategy, and sometimes I also talk about an adversary, perhaps, but a strategy is simply a mapping which takes a history, that is a finite computation, which finishes with a state of some player, and then it returns a probability distribution over the decisions. This, of course, includes as Dirac distributions also the deterministic choices. So I can talk about strategies being deterministic or randomized. I can talk about memoryless strategies if they are history insensitive. I can also talk about finite memory or infinite memory strategies. But a strategy profile, if you have n players, is a vector of n strategies, one for each player. Now, for a strategy profile, once you fix the strategy profile and a stochastic turn-based game, you can derive a Markov chain. It will be an infinite state Markov chain where the states of that chain are going to be simply the finite histories. And we can then derive a probability measure, standard probability measure over that, and it allows us to reason about the probability of events. And it also allows us to reason about expected rewards. Because the samples in my probability space are infinite computations, I can define a random variable which gives me the reward for each sample and take the standard expectation for the probability measure. But I also need to write down the properties. And for this, I need a property specification language, and I'm resorting to temporal logic. And this temporal logic, RPATL, stands for Reward Probabilistic Alternating Temporal Logic. And it's a hybrid. It's a hybrid of ATL, because it has the coalition operator of ATL. But on top of that has the probabilistic operator, like the one that I showed you, which is from PCTL, the probabilistic version of the computation tree logic. And it also has a reward operator. So the probabilistic operator computes the probability, compares it to the bound, and the reward operator computes the expectation and compares it to the bound. Now with this I can express properties, for example, that players 1 and 2 in a coalition have a strategy to ensure that the probability of an error occurring within 10 steps is less than 0.1, regardless of the strategies of other players. And I can then formally write down the language where, like in PCTL, I have phi is a state formula, and it expresses the coalition, and I can talk about the probabilistic operator reward and ratio rewards. The reward operator takes a formula which either expresses long-run average or the total cumulative total reward. I can now talk about, well, players in coalition C have a collective strategy to ensure that the game reaches an end state, almost surely, regardless of the strategies of other players. Now, I want to have a model checking algorithm for that. I also can represent the reward properties. So the semantics for most operators is standard. So here, I just want to tell you what the semantics for the P and the R operator is like. Since I have introduced the concept of a coalition, I'm interested in strategies for the coalition against strategies of everybody else. So I can simply reduce a multiplayer game to a two-player game where player 1 is the coalition and player 2 is everybody else. And then I can say that this property is true for some coalition C if in the coalition game there exists a strategy for the coalition such that for all strategies of everybody else, I win. The coalition wins. Okay? So this is a very natural interpretation. And just to see whether you are awake, this is an example of a stochastic multiplayer game. And the first question is, does that player have a strategy to get to the jackpot with probability a quarter? Yes. Right. What about probability at least 1/3? No, because it can be prevented from doing so by the other players. But, of course, the yellow player can enter into a coalition with either the blue or the green player, and then it can increase. Okay, so the reward is then for a coalition, not for an individual player. So that's the idea. And for these stochastic multiplayer games, we studied two fundamental problems. One is the verification problem, which is defined as the existence of a strategy for the coalition which is winning against any adversary. Notice that this is rather different from, for example, working with MDPs, which have a universal interpretation for all strategies you want to obtain some reward. But here there exists a strategy. Now there is also the synthesis problem. Assuming such a strategy exists, can you find one? So I want to go from A to B, minimizing the cost. Can you find me a strategy? Now it turns out that both players, we've reduced to 2-player games, they have optimal strategies. And for the logic fragment, without step-bounded, memoryless deterministic strategies suffice. And I can also construct the strategies. I employ value iteration. So this is actually exactly as it was done by Anne Condon for what she called simple stochastic games. But are single objectives enough? And the point I'm trying to make here is no. So if you think about the Google car, there is always an overriding objective, which is safety. We don't want any crashes. We don't want to hit an oncoming car. But there will also be other objectives, and you would want these objectives to be satisfied simultaneously. So instead of considering just single objectives, I want to allow the possibility of multi-objectives, or sometimes also called multidimensional. And I'm going to restrict just to conjunctions. Okay? So the idea is that I have 2 such objectives, but each comes with a different probability of or reward bound, and I want to meet both these at the same time. So I want a strategy which will meet the reward, the bounds for each component. Now, for many applications, conjunctions are enough, but if you want to have this kind of reasoning for assume guarantee, then you need to go and you will need Boolean combinations. So the tool is not restricted to conjunctions, I'm just simplifying. I'm also simplifying the presentation by showing you an example of a Markov decision process rather than a game. And in this Markov decision process, I have a conjunction of properties. I want to reach D with probability at least 0.2, and I want to reach E with probability 0.6. I have 3 actions, but notice that deterministic strategies are not enough, because the deterministic strategies are represented here, okay? But they do not meet both bounds simultaneously. In fact, what I have to work with is randomized strategies, and that's already the case for MDPs. So I have to work with randomized strategies, and this strategy is one that meets these. Now, the shaded area represents all randomized strategies, and the dark blue is the Pareto front, or the Pareto curve, which gives me the optimal points. So these are pairs of values where you cannot improve one without decreasing the value of the other. And with this approach, what I can do is I can then explore the trade-offs. So whichever point you choose here corresponds to a different weight of the combination of these 2 deterministic strategies. And this is perhaps something that the designer may want to choose. Now, this was for MDPs. For MDPs, optimal strategies exist, but randomized strategies may be needed. The situation for stochastic games is much more complex, because even optimal strategies may not exist, and I may need infinite memory. So I have to work with restricted games, and I also work with stochastic memory update representation, which is a more succinct representation. If you are interested in this, I can explain this in the break. It has the same power as the notion of the strategies that I've given you, but it is more succinct. In particular, it's enough to work with finite ones, which is not enough for the other ones. So now I'm showing you an example of a Pareto set, which you can obtain from the tool. And this is also a snapshot, from the tool, which can work with n objectives in general, and it will support slicing, projections, and slicing to 2D. But what we also support is compositional strategy synthesis. That is not compositional verification, but compositional strategy synthesis. This is because, of course, this state space explosion is a huge problem. And if I have a game which is built from a number of components, then I have the exponential state space explosion. And these games very quickly become too much for the poor tool to cope. So the idea is to introduce assume guarantee reasoning, where if you have two games, game 1 and game 2, if one guarantees phi A and the other one guarantees phi B, but under the assumption that phi A is satisfied, then you can deduce this global property for the parallel composition of the game, which you do not actually have to construct. You do not have to construct. This is not a straightforward operator for games. Just think about how you'd combine two local states when you have different players. So this is not a straightforward thing, and something that has not been studied much in, for example, in concurrency theory, developing these types of operators. So what we can do with the assume guarantee rules is we can construct strategies for the composition, for the global system, by composing local strategies. This is at the cost of expressiveness. I will not be able to obtain every strategy, but it gives me an under approximation of the Pareto set, but it improves the speed of analysis. And this is what this kind of reasoning would do. So there is the tool which is called PRISM-games. And it is an extension of PRISM. Currently, it is explicit state, but there is work in progress on developing a symbolic implementation, which is much quicker in terms of the model construction. And there have been several case studies. So even though I showed you games which are only discrete state, discrete time, and discrete probabilities, we have also considered games which you obtain from stochastic hybrid systems, but you have to do it by discretizing. So far, what I hope I have shown you is that in order to model this competitive and cooperative behavior, as on the road, Google cars, or collaboration between robotic assistants and humans. And I have also mentioned that there is a tool to support it, but the final question I wanted to ask is this going to be sufficient? I've already argued that we should switch away from MGPs towards stochastic games. That's a huge complexity, but can we really just work with games? And again, if you are following the news, it is becoming very clear now that games on their own will not suffice. Now, if a human has to negotiate something, or another car has to negotiate something with a Google car, they need very complex multimodal communication. And that's something that the robotics community is looking at. But we also need to consider the cognitive reasoning processes that the human goes through, because we have to make these cars more like human. So you need to introduce cognitive architecture. There are also social norms, trust. The Tesla car crash has been described as the case of overtrust. So a provocative question, can we do quantitative verification for trust? Morality is another one. If you are letting a robotic assistant into an elderly care home, how do you make sure that these behave ethically? So it's not that simple. But another gap that I wanted to mention, and here I'm very grateful to my collaborators from the Oxford Robotics Institute. That's a joint project that we have, and I'm very grateful for introducing these great problems for me to study. Perception software. Perception software relies on machine learning, deep learning, for example. And this is a picture that I'm showing you. This is the technology that was developed at Oxford. And it builds a point cloud. It uses LiDAR. And it first learns a map by driving a car around it, and then the idea is that if the car drives itself, it has access to the map, but also in real time needs to be able to tell the difference between the car, a motorbike, or a pedestrian. Okay, and for this, they are using machine learning, not yet deep learning, but they are working on deep learning and developing an end-to-end, which is a complete machine learning solution, no logic. Now, of course, there are many things that can go wrong in perception software. You can have a sensor failure, but you can also have an object detection failure. And machine learning software is not very clear how it works. And also, for us verification people, we're obsessed about guarantees, but machine learning algorithms don't provide any hard guarantees. So this is a topic that I intend to study and perhaps tackle the issue of doing formal verification for these kinds of modules. So this brings me to the conclusion. And so far I have introduced stochastic multiplayer game as a modeling abstraction for mobile robotics, mobile autonomy. But the work so far has focused on properties like safety, efficiency, both in a single and multi-objective case, but there are many things that we have not even started to tackle. So, for example, partial observability, that's not handled by the tool. I've mentioned perception software, but also, since we are talking about games, the logic that I've mentioned actually gives you Nash equilibria, but it doesn't give you all the interesting Nash equilibria. So some combination with which would give you the right Nash equilibria is interesting in the combination with mechanism design. And the observation is that even building on top of these games, we need to extend them with cognitive reasoning and perhaps even social aspects, human-like trust. And the big question for me is, can we develop quantitative verification and synthesis techniques? What synthesis? Think of a counter strategy. So I want to avoid, some flaw. I may want to develop a strategy. Ask the tool to give me a strategy to avoid a crash. So that's it. And I wanted to acknowledge my collaborators, too many in this, so I didn't put all the names, and the funding. Okay, thank you.
Time for questions?
At the beginning you said that you have a frequentist interpretation of probability rather than Bayesian. How this reflects in your model? What would change if it was Bayesian instead?
Okay. I mean, so I wasn't telling, I mean, in the work behind PRISM, all is based on the frequentist interpretation, but actually we are developing something where we do take the Bayesian approach as well. So if I can give you an example, I think appealing to this, I need a prior, and I work with states which are probability distributions. These probability distributions can, for example, be GPS data. There is a data type now developed called uncertainty, which represents these distributions. And yes, then starting from the prior, I can do inference. And I mean, I have to say that my tool is incredibly slow compared to, I think, what we heard about in the first talk. So if we can learn and adopt some techniques from AI, then we haven't tried them CMC.
The way you collect the probability.
Yes, yeah, and I mean also in the way that the probability measure is defined. It is defined based on the frequentist. What do you mean, the probability of getting somewhere? But I can redefine it. I can still define a model for the dynamics. I just need to change the notion of the state and transitions between the states.
Maybe one more quick one.
It would seem like there's almost a direct contradiction between a model checking approach and dealing with probabilities. Because in model checking, you're assuming everything's known. And so they just seem incompatible on the surface.
Yeah, no, I guess that's right. That is a very good point. I mean, what's logic? Logic is about 0 and 1, true and false. Yes. So in this case, I get true and false by computing the probability and comparing it to the threshold. So that's my true and false. But I can also take a quantitative interpretation. I can simply ask the tool to give me the probability or the expectation. And in fact, this was an afterthought, but this is something that we've added to the tool because people wanted to use it that way.
All right, let's thank Marta one more time. We have a break now. Check the screens for the updated schedule.